Hello, welcome to Basic Bioelectronics Class 2. We have already come to know that bioelectronics is essentially the result of cross-fertilization between electronics and biology. That is why there should exist some sort of analogy between electronics and biological materials, so that both materials can be cross-fertilized. Let us first see some properties related with semiconductor materials. This is simply an overview because it is assumed that you have already come to know about some basic properties of semiconductor materials. Because you know that in case of semiconductor materials, when two or more atoms form a molecule, as when two hydrogen atoms and one oxygen atom combine to form a water molecule, the forces that bind the atoms together within the molecule are called covalent forces, and the interatomic bonds formed are called covalent bonds. Covalent bonds are, you know that these are chemical bonds which are characterized by the electrons being shared between two or more atoms, so that the discrete nature of atoms is lost. A characteristic of covalent bonds is their directionality. They are directed or oriented at well-defined angles relative to each other. Due to this orientation, we get a perfectly ordered diamond structure made by carbon atoms and crystalline structure made by silicon atoms. Let us take an example. Semiconductor crystals are held together by covalent bonds, that is highly localized short range bonds. It is less than 1 nanometer. So here the covalent bond in silicon semiconductor is shown here. The 4 valence electrons of the outermost orbit of each atom are being shared by neighboring atoms. Here the orientation of at theta equal to approximately 110 degrees is shown. That is why a crystalline silicon structure is obtained. This is basically covalent bond. Here electrons are shared by the neighboring atoms. And the gap energy is so in semiconductor, especially in case of intrinsic semiconductor, gap energy is so small that even at ordinary room temperature, there are many electrons which possess sufficient energy to jump across the small energy gap between the valence band and the conduction band. In a piece of semiconductor, under equilibrium conditions at temperature T greater than the absolute zero, there is a fixed concentration of charge carriers, which are electrons and holes. A recombination event takes place when a free electron combines with a hole to complete the valence structure on a local basis. Let us see the charge concentration in intrinsic semiconductors. Let n be the number of electrons in conduction band per centimeter cube, that is the free electron concentration. P is be the number of holes in valence band per centimeter cube, that is free hole concentration. Ni be the equilibrium electron concentration in intrinsic semiconductor. Pi is the equilibrium hole concentration in intrinsic semiconductor. Thus, obviously, N equal to P equal to Ni equal to Pi. That is why Np equal to Ni square, because N equal to P. N equal to P equal to Ni into Ni equal to Ni square. The fixed concentration of electrons and holes in the respective bands results from the balance between the rate of generation of electrons and holes and the rate of their recombination. For this, it is reasonable to assume that capital R equal to small r Np, or capital R equal to small r Ni square, where capital R is the recombination rate in electron-hole pairs per centimeter cube, and small r is a proportionality constant in centimeter cube per second. This law is called mass action law and can be stated as: at any given temperature, there will exist one particular concentration of holes and electrons at which the recombination rate and the thermal generation rate, that is Gt intrinsic, are in balance. That is, generation rate Gt intrinsic equal to recombination rate equal to R Ni square. Now suppose we dope it with donor impurities. Let donor impurities per centimeter cube equal to Nd. Due to donor impurities, the semiconductor will become N-type material, N-type semiconductor. As a result, the concentration of electrons and holes in the respective bands will change due to doping. Let N subscript N be the electron concentration, it is the nu due to doping. Pn hole concentration, nu due to doping. So to maintain electron and hole concentration in a steady state conditions, electrons and holes should recombine at the same rate as they are generated. Let the new generation rate be Gt dope. And since the rate of generation is the same, therefore Gt dope equal to Gt intrinsic, or N and Pn equal to Ni square. This equation means that if we increase the electron concentration from Ni to Nn by adding donor impurities, the probability for recombination of the hole will increase, with the result that the equilibrium hole concentration will be reduced from Pi to Pn. And to have electrical neutrality in the crystal, we require that Qnn equal to Q into Nd plus Pn, or Nn equal to Nd plus Pn. So we have now two independent equations. One is Nn Pn equal to Ni square, and other is Nn minus Pn minus Nd equal to 0. Now combining this equation 2.1 and 2.2, we have Nn square minus Ndnn minus Ni square equal to 0. This is actually 2.1 and 2.2. These two equations, combining this. So solving this quadratic equation, we have Nn equal to Nd by 2, that is new electron concentration. Nd by 2 plus Nd square by 4 plus Ni square within bracket root over. Let us take an example. Suppose we have to calculate the carrier concentration in phosphorus doped silicon crystal at room temperature and at 100 degrees centigrade. The concentration of phosphorus atoms is 10 to the power 18 atoms per centimeter cube. That is, it is Nd equal to 10 to the power 18 atoms, donor atoms. So also assume that intrinsic electron concentration at 25 degrees centigrade is 10 to the power 10 per centimeter cube, and at 100 degrees centigrade 1.5 into 10 to the power 10 per centimeter cube. We have to find Nn and Pn when Nd equal to 10 to the power 18 per centimeter cube. From the generation recombination balance at any temperature, we know that Nn Pn equal to Ni square. At 25 degrees centigrade, Nn Pn equal to 10 to the power 10 into 10 to the power 10 equal to this 10 to the power 20 or Cm6. Now using equation 2.4, this is Nn equal to Nd by 2 plus Nd square for this one equal to, if you put, you will get 10 to the power 18 per centimeter cube. Then you use the equation Pn from here, this equation Pn equal to Ni square by Nn. You will get the whole concentration, new whole concentration at 25 degrees centigrade, which is equal to this one. Therefore, at 25 degrees centigrade, Nn, the new electron concentration will be this, and whole concentration will be this. Similarly, proceeding like this, using the same equations, at 100 degrees centigrade, you will get new electron concentration as this, and new whole concentration at 100 degrees centigrade will be this much. This is for N-type semiconductor material. Now let us find the charge concentration in extrinsic semiconductor, which is P-type. P-type material, how can we get? By doping trivalent atom. Let us consider silicon crystal that has been doped with Na acceptors per centimeter cube. So whole concentration is Pp per centimeter cube, and electrons concentration is Np per centimeter cube due to acceptor atoms. So exactly proceeding like the previous, this for charge neutrality, Qpp equal to Q Na plus Np, or Pp equal to this much, or Pp equal to this much. Again also Np, Pp equal to Ni square. From these two equations, we will get this quadratic equation 2.5. So solving this, we get the new whole concentration due to acceptor is this. So you try to solve this problem. Calculate at room temperature and at 100 degrees centigrade the carrier concentrations in a boron doped silicon crystal, where the concentration of boron atoms is 10 to the power 18 atoms per centimeter cube. Assume this 25 degrees centigrade, and at Ni 100 degrees centigrade this much. You try yourselves. So carrier, as far as carrier motion in semiconductor is concerned, there are basically three basic processes by which electrons and holes move in a semiconductor. These are drift, diffusion, and recombination generation process. Drift, what is drift? It is the net displacement of carriers due to application of an electric field. That is, when electric field is applied across the semiconductor crystal, the current that you will get due to the developed electric field, that current is called drift current. And since semiconductor, so two types of carriers we will be getting. One is due to and other is due to P, holes. And diffusion, here also carrier displacement due to concentration gradient. That is the flow of charge from a region of high density to a region of low density. It follows Fick's law, especially applicable in case of, mostly applicable in case of p-n junction. So the formation of depletion layer. Also recombination and generation. It is a process by which electrons and holes are created. Recombination is a process by which electrons and holes are destroyed. It is a balancing process for carrier generation. It is thus not directly responsible for carrier motion, but affects the transport of the carriers. So as far as Dept current is concerned, the electric field E in a direction, say X direction, due to an applied voltage across a sample of semiconductor material, causes carriers to move in opposite directions. That is, if holes move in one direction, then electron will move in another direction. But as a whole, total current will be sum of both. Now electron Dept current density is given by equation 2.7. Q n mu n Ex, where Ex is the electric field in the direction of X. Q is the elementary charge, n is the electron concentration, and mu n is the mobility of electron. Similarly, the whole Dept current density is given by equation 2.8. And the total Dept current density in X direction is given by sum of 2.7 and 2.8. That is, the total Dept current in X direction equal to Q into this, represented by equation 2.9, where mu n and mu p are mobility of electrons and holes respectively, and the unit of mobility is cm square per volt second. N and p are electron and hole concentration respectively. Diffusion current. Exactly same way Fick's law is applicable. Using this Fick's law, the total electron and hole diffusion current density in the X direction is given by equation 2.10. That is, total current density due to diffusion is equal to Q into dn dx minus dp dx, where this dn and dp are diffusion constant of electrons and holes respectively, given by dn equal to kT by q mu n, dp equal to kT by q mu p, which are known as actually Einstein's relation. Transport equations. In semiconductor device, these two currents, Dept and diffusion, are present simultaneously. That is, both are present at the same time, and therefore total whole current density will be given by sum of Dept current in the X direction, sum of diffusion current in the X direction. Similarly, the total electron current density in X direction will be given by equation 2.14. This expressing 2.13 and 2.14 in three-dimensional forms, we get this equation 2.15 and 2.16. These equations, that is, it is a vector operator, del by del x, del y by del y, del by del z. and equations now 2.15. So equations 2.15 and 2.16 are known as the transport equations for holes and electrons respectively. Thank you.